Hey guys, today I will explain about some properties of liquid and solids. First material, vapor pressure. When you fill a drink bottle with hot water, it's also filled with steam. But to the incident not happen for long, the event was a result of the evaporation process and the decrease in vapor pressure. Look at this, the picture. In the next phase, the particle occur from liquid to gas phase. But there is a change with particle phase from the gas to the liquid phase. If for solvent is fed into a closed place, there will be a transfer of particle from the liquid phase to the gas phase, and the vice versa. The amount of four solvent particles in the gas phase give a pressure called vapor pressure. After some time, the number of four solvent particles escaping from the liquid phase to gas phase is the same as the number of four solvent particles in the gas phase trapped on the surface of the liquid phase. In time like this, it can be said that dynamic equilibrium has been achieved. In general, vapor pressure can be divided as follows. Vapor pressure is the pressure of vapor at equilibrium with its non-vapor phase. All solid and liquid have tendency to evaporate into a form of gas. All gases have a tendency to condense again. At a certain temperature, a certain substance has a partial pressure, which is the dynamic equilibrium point of the gas of the substance in the gas, liquid, or solid. From this point is the vapor pressure of the substance of the temperature. Second, solution for vapor pressure. Solution for vapor pressure. If a solvent is added to a four solvent, what will happen to vapor pressure value of the solution? From the explanation, we can see that the pressure of the solution is actually smaller than the vapor pressure of the four solvent. This is actually what is meant by the reduction in vapor pressure, or delta V of the solution. The reduction in vapor pressure is the reduction in vapor pressure of a solution relative to the vapor pressure of four solvents. The value delta V can be calculated from the vapor pressure of the solution described by rule Frenchius and is known as rule law. The formula rule law: V solution equal X solvent V solvent. Delta V equal V solvent minus V solution. V solvent minus X solvent times V solvent equal V solvent times 1 min X solvent. Delta V solvent. So the formula delta V equal V solvent times X solute. And then delta V decrease in vapor pressure. VO solvent vapor pressure of For a solvent, X solutes mole fraction of the solutes. Vapor pressure. If a quantity of pure liquid is placed in an effective container that has a volume greater than that of the liquid, a fraction of the liquid will evaporate so as to fill the remaining volume of the container with vapor. Provided the sum liquid remain of the equilibrium is established, the pressure of the vapor in the container is a function only of the temperature of the system. The pressure developed is the vapor pressure of the liquid, which is a characteristic property of a liquid. Increase rapidly with temperature. The temperature at which the vapor pressure is equal to 1 atm in the normal boiling point of the liquid Tb. Some solids are sufficiently volatile to produce a measurable vapor pressure even at ordinary temperature if it should happen that the vapor pressure of the solid reaches 1 atm at a temperature below the melting point of the solid. This temperature is called the normal sublimation point. Ts. The existence of a vapor pressure and its increase with temperature are consequences of the Maxwell-Boltzmann energy distribution. That is, a large molar heads of vaporization Q5 at 20 derajat Celsius. The heads of vaporization of water is 44 kg per mole, while the of carbon tetrachloride is 32 kg per mole. The vapor pressure at this temperature are 2 times 30 kVA for water and 12 times 13 kVA for carbon tetrachloride. V equal 0. N equal a x min V for RT, where A is a constant. V equal Vx min V for RT, where V is the another constant. Q5 is related to V by Q5 equal V plus RT, where V in the expression for V. V equal V rho A times A minus Q5 for RT. V where V is also a constant. The constant V has the same units as V and can be evaluated in terms of the Q5 and the normal boiling point Tb. At Tb, the vapor pressure is 1 atmosphere, so that's 1 atm equal V E times E minus Q5 for RTV. Then V equal 1 atm times E plus Q5 for RTV. Suffices to evaluate the constant V. Ln V equal min Q5 divide RT plus ln V rho. Okay, the next material, other properties of liquid. The viscosity, or more precisely the coefficient of viscosity of a liquid, measure the resistance to flow under stress. Because of molecules of liquid very close to one another, a liquid is much more viscous than a gas. The close spin and the intramolecular forces both contribute to this resistance to flow. The move a molecule from the body of the liquid, the surface requires the addition of energy. Since the presence of another molecule in the surface increases the surface area, it follows the energy must be supplied in increase the area of the liquid surface. The energy required to effect an increase of 1 meter cubic is called the surface tension of the liquid. All liquids show the following characteristic. 1. Liquids are almost incorporeal. In liquids, molecules are pretty close to each other. The molecule doesn't have a lot of space between them. The molecule cannot squeeze close to one another. 2. Liquids have fixed volume but no fixed shape. They have fixed volume but they do not have the fixed or definite shape. Example, if you have take 1000 milliliter of water, for water is a cup, is the will take the shape of the cup? No, for the liquid from cup out of bottle, the liquid has changed its shape and now it has taken the shape of bottle. 3. Liquid flow from higher to lower level. 4. Liquid have their boiling point above room temperature under normal condition. The liquid on heating slowly change to vapor or gaseous phase. The process is called boiling. Okay guys, the last material, structural differences between solid, liquid and the gases. Look at this picture. The diagram below illustrates the molecular arrangement in their phase of matter. This is gas, liquid, solid. Gas. In the gaseous phase, the molecule mentioned dominant. The molecules of the substance are completely separated and move about independently of each other. The space between the molecules are very large compared to the size of the particles, so that a measured volume of a gas is actually a measurement of the space between molecules. Liquid. In comparison, the molecular structure of liquid phase has some space between the particles that allow the particle to move fast one another. But attraction between the particles is strong enough to prevent them from moving very far apart. And then solid. In the solid phase, the forces of attraction have completely overcome molecular motion. The movement of the particle has been reduced to vibrating in the place. The particle cannot move past one another and held in a tightly fixed pattern, so there is very little space between the particles. Since in a liquid the molecules are separated by a distance of the same magnitude as the molecular diameter, the volume occupied by a liquid is but the same as the volume of the molecules themselves. At thus close distance, the effect of the intramolecular forces is very large. With the result, the H molecule has a low potential energy compared with its energy in the gas. The difference in potential energy between gas and liquid is the energy that must be supplied to vaporize the liquid. The mass of the molecule in the liquid is still quite but since the liquid occupies a much smaller volume, there is less randomness in the spec distribution of the molecules. The molecules in a solid are located in a regular pattern. The spatial arrangement is not random as in the gas or liquid but conventionally ordering. The solid does not follow under the application of small stress as do liquid or gases, but they form selectively snapping back when the stress is removed. The distribution of energy solids in solid and liquid essentially the same as in the gas, and so long temperature sufficiently high is described by the Maxwell-Boltzmann distribution function. The method in gases is characterized by kinetic energy only. Solid and liquid there is potential energy as well. The method in solid consists fully of vibration. In liquid, some of the molecules are moving the liquid while others are momentarily checked by their neighbor and vibrating in the check.
What you're given, that's how we live it. Don't be mad at the system, it's simply how we've existed.